Hi, this is Ben Tupper. In this video, I'm going to illustrate a proof of a theorem of topology. If you have a copy of Walter Rudin's Principles of Mathematical Analysis, you can follow along in Chapter 2, Theorem 234. The argument is Rudin's, but the wording and illustrations are my own. The theorem states, compact subsets of metric spaces are closed. Here are some terms you'll need to be familiar with in order to understand the proof. A set is compact if every one of its open covers contains a finite subcover. And a set is closed if it contains all its limit points. You can also say a set is closed if its complement is open. Let's get to it. Compact subsets of metric spaces are closed. Proof. Let's start with a sketch of what we're going to do. Consider a compact set K. We want to show that K is closed in our metric space. To do that, we'll show that the complement of K, that is, everything else, is open. And to show that the complement of K is open, we'll show that all of its points are interior points. So for any point P not in K, we want to show that there's always a neighborhood around it that does not intersect K. That is, P has some room to wiggle, and it won't touch K. This will show that P is interior to K complement, which will show that K complement is open, which will show that K is closed, as desired. Can we show that such a neighborhood always exists? Obviously, because Rudin said so. We're going to find this neighborhood by first turning our attention to our compact set K. Pick a point in K. Call it Q. Now place a neighborhood around Q. Call it W sub Q. We'll let the radius of this neighborhood be half the distance from Q to P. So if Q is farther from P, it will have a larger neighborhood, and if it's closer to P, it will have a smaller neighborhood. We will also associate with this point Q another neighborhood of the same radius, but this one around P. Call this V sub Q. Remember, even though the subscript is Q, V sub Q is a neighborhood around P. The subscript Q just refers to the point that gave it its radius. So for a point Q in K, we have two associated neighborhoods. The one around Q, I'll draw that in yellow, and the one around P, I'll draw in green. Notice that the two are disjoint. They share no points in common. Let's clear the slate. Using the procedure we just outlined, we're going to start by placing a neighborhood of appropriate size around every point in K. This might generate an infinite number of neighborhoods. Don't make me draw them all. The important thing is that we have a collection of open sets that completely covers K. In building this cover for K, we get a collection of corresponding neighborhoods around P. Now, it would be nice if we could take one of those, maybe the smallest, and say, look, I have found it. This neighborhood is in every other green neighborhood that we constructed around P. So it's disjoint from every yellow neighborhood around points in K. And so, more importantly, it's disjoint from K. Ta-da! P is interior to K complement after all. Not so fast. The problem is, what if there are an infinite number of these green neighborhoods around P? How do we even know there's a smallest one? What if their radii just approach an infimum without actually attaining it. Here's where we use compactness. We've defined an open cover for our compact set K. It's the collection of neighborhoods W sub Q for all Q in K. By compactness, we know that we can throw away most of these neighborhoods, keep just a finite few, and still have a collection of open sets that covers K. Let's call this finite collection W. Now we have a way of winnowing down our possibly infinite collection of neighborhoods around P. For each neighborhood in W, we choose its corresponding neighborhood around P. Since W is finite, this collection is finite too. Finally, we're ready to take it home. We now have a finite collection of non-empty sets. So its intersection, let's call it V, is also non-empty. And since V is contained in every set of that collection, it doesn't intersect any set in W. W covers K, so we can be sure that V does not intersect K either. That makes P interior to K complement, which makes K complement open. K is then closed. Q, E, D.